Hello and welcome to another eMathInstruction Common Core Algebra 1 lesson. I'm Kirk Weiler, and today we're going to be doing Unit 9, Lesson number 5, Finding Zeros by Completing the Square. As always, you can find the worksheet that goes with this lesson along with an accompanying homework by clicking on the video's description. Don't forget that at the top of every one of our worksheets has one of those great QR codes that you can scan with your smartphone or your tablet, take you right to this video. Alright, well let's get into the substance of today's lesson. Today what we're going to be doing is we're going to be trying to find the zeros. And remember, the zeros are also known as the x-intercepts of a function, and we're going to be concentrating on quadratics today. Specifically, we want to figure out where the output to the function is 0. Sometimes that's easy, sometimes it's more difficult. It all kind of depends, especially if the function is written in that standard form, ax squared plus bx plus c. Now we're going to be looking at how we can find the zeros, not by factoring and using the zero product law, but by using the method of completing the square, which we learned earlier in the course. Let's get right into our first exercise. All right, in the first exercise, they give us a quadratic, y equals 2 times the quantity x minus 2 squared minus 36, and we want to find the zeros in simplest radical form. Watch out for that buzzword. It oftentimes means that your answers are going to turn out to be kind of ugly, have radicals in them. So let's do it. Let's take our function, and anytime we're looking for the zeros of a function, the first thing that we want to do is take the function and set it equal to 0. Now, because our quadratic is written in vertex form, what we can do is we can undo what has been done to x. Remember solving these using inverse operations? So we've subtracted 2 squared, multiplied by 2, and subtracted 36. So the first thing I'm going to do is add 36 to both sides to undo that subtraction, right? That's going to give me 2 times x minus 2, quantity squared equals 36. Then I'm going to undo that multiplication by 2 by dividing both sides by 2. That'll give me x minus 2, quantity squared is equal to 18. Now I'm going to undo the squaring by taking the square root of both sides. And remember, probably the easiest thing for students to forget is the fact that they need to introduce a positive and a negative solution at this point. Now, if the question didn't say put our answers in simplest radical form, I might leave the square root of 18. But I'm going to bring this up here. I'm going to change this into x minus 2. Remember how we simplify a radical. We find the largest perfect square that goes into the radicand, the number underneath the square root, and that's going to be 9. And now I can take the square root of 9, leave that plus minus there. I get plus minus 3 times root 2. The last thing I have to do is add 2 to both sides. Now this can be a little tricky, visually tricky, because it would be really tempting to do 2 plus 3 and get 5, but in fact we're just going to get 2 plus or minus 3 times the square root of 2. We can't combine the 2 and the 3 radical 2 because they are not like terms. One of them is a rational number. This is rational. And as we've already seen, this number in total is irrational. Now, in real applied settings, most of the time, we want to know what the zeros are in some kind of decimal form. That's pure calculator work. So if we take our calculator out and we type in 2 plus 3 times the square root of 2, got to be really careful there, but it should work out nice. And if we round to the nearest tenth, we'll get 6.2. And if we do 2 minus 3 times the square root of 2, we'll get negative 2.2. I didn't break out the calculator on this one to show you how to do it because I thought that would take too much of our time, but hopefully you can get these two answers if you start with your 2 in simplest radical form. Now, that's something that we've done before already. All right, in exercise number 2, what we're going to do is we're going to kind of compare and contrast. See, we've already found zeros in a different way, and that was by factoring. Okay, so let's take a look at exercise number 2. We've got a quadratic, x squared minus 6x minus 16. And we want to find its zeros, so we're going to set it equal to 0. But we're told that we have to do it by factoring. In other words, we're going to use what's known as the zero product law. So maybe I do some guessing and checking. All right, maybe you do some guessing and checking. What I'd like you to do is take a moment, take up to 5 minutes, and guess and check and figure out how that trinomial factors. All right, let's go through it. Hopefully what you found out was that it factors as x minus 8 and x plus 2. Remember, all we really have to do when we check our factoring is make sure that this times this, which is negative 8x, and this times this, which is a positive 2x, sum to be negative 6x, right? But we do need to check that. Always check it. Now remember how the zero product law works, right? It says, well, if I've got something factored and set equal to 0, either that factor is equal to 0, or this factor is equal to 0. Either x minus 8 is equal to 0, or x plus 2 is equal to 0. Easy enough now to add 8 to both sides, and we'll get x equals 8. And subtract 2 from both sides, and get x equals negative 2. Right? So those are our two zeros of this quadratic, negative 2 and positive 8. Now I claim that you can also find these the way that we did it in exercise 1, but by completing the square. The thing that's of course challenging is that our quadratic here is not written in vertex form. All right, so let's take a look at how we can do that. Let's take x squared minus 6x minus 16 and set it equal to 0. Now your teacher may show you a slightly different way of doing this. I have my own particular way. What I like doing, remember how completing the square works, is we only concentrate on the first two terms. Now it only works if a is equal to 1, and a is 1 here. We take half of our b term, which is negative 6, and we square it. And we add it on, plus 9. Now remember, how I do this is I add 9 and I subtract 9 at the same time, because when you do that, then all you're doing is adding 0, and that's always okay. Can't lose that negative 16. All right? So these two equations are equivalent to each other. But the beautiful thing now is that this expression is a perfect square. It's x minus 3 squared. We can combine these two. There'll, of course, be negative 25. And now we've turned our quadratic into something in vertex form. Okay? We can now solve it the way that we did in exercise 1 by undoing what has been done to x. I'll add 25 to both sides. I'll get x minus 3. Quantity squared equals 25. I'll take the square root of both sides. I'll write my answer up here. X minus 3 equals, don't forget, plus or minus 5. So there's two equations here, right? There's x minus 3 equals a positive 5, and if I add 3 to both sides, I'll get x equals 8. That's a good thing. We knew that we were going to get 8. And if I get x minus 3 and set it equal to negative 5, and add 3 to both sides, I'll get that other 0. X equals negative 2. Now what I've found out as being a math teacher over the years is that very often students, once they learn one way of doing a problem or solving a problem, they don't like to learn another way, right? And I get that, right? Once you know one way to do something, it's nice to be able to just master that way. Learn it, understand it, and use it. But it's good for us to be able to find the zeros both by factoring and by completing the square. And we're going to see why that is in the next problem, okay? I'm going to clear out the text, so copy down anything you need to. Okay, here we go. Let's move on. Exercise number 3. Let's take a look at the quadratic x squared plus 6x plus 2. Letter A, it says, find the zeros of this function using the method of completing the square. What kind of numbers are the solutions? So I'm going to ask you to pause the video right now if you feel confident about finding the zeros using completing the square starting in this form. If you don't feel confident with it, I think that's understandable. Maybe watch me do another one, but pause the video now if you want to take a shot at this on your own. Okay, let's go through it. All right, first things first. You want to find the zeros. I want you to set whatever function you're working with equal to 0. Not the x, but the y. All right, now we're going to do this by completing the square, so we're going to take half of 6, we're going to square it, and we're going to add it on. Half of 6 is 3, square it, and we get 9. Immediately, I'm going to subtract a 9 as well. That means overall, I'm adding 0, right? We can always add a whole lot of nothing. I can now factor this as x plus 3, quantity squared. I can now combine these terms as negative 7. All right, let me pause there for a second. Just make sure you're up to speed. All right, now we can solve this by just undoing our order of operations. I'm going to add 7 to both sides. I'll get x plus 3, quantity squared equals 7. I'll take the square root of both sides, write my answer up here. X plus 3 is plus or minus square root of 7. Now let's pause for a second. You should feel comfortable enough with perfect squares to know that 7 is not 1. It's not a perfect square, right? It's not 1, it's not 4, it's not 9, it's not 16, not 25, right? So the best thing that we can do with the square root of 7 is just leave it unless we're told to write it in simplest radical form. And even if we were, we would still leave it because it's as simple as it can get. So the only thing I'm going to do right now is subtract a 3 from both sides, and I'm going to get an answer that seems very strange, right? Negative 3 plus or minus root 7. Don't combine. Don't combine. Now, the question also asks us what kind of numbers our answers are. Well, remember, whenever we have a rational number, which negative 3 is, plus or minus an irrational number, our answers are irrational. Anytime we add rational to irrational, we get irrational. That really goes to why we can't combine the two, right? It's kind of like combining unlike terms. You can add an integer to an integer, and get something that works out fine. But a rational number plus an irrational number, you either have to express as a rounded decimal, all right, if asked, or you just have to leave the two, all right? Now, let's try to solve this by factoring, okay? Well, not try to solve it by factoring, but try to factor this thing. Now, if we're making smart guesses on our factoring, right, then there's really only two guesses we can make. We can either make x plus 1 times x plus 2, because remember, these two terms have to multiply to be this, and these two terms have to multiply to be this. Yeah, but the problem is, right, that's a positive 1x. This is a positive 2x, and when they combine, 1x plus 2x gives me 3x. And that just isn't 6x. The only other even somewhat reasonable guess, and you could argue that it's not reasonable at all, would be x minus 1 times x minus 2, because again, it gives us that x squared and that positive 2, but it's going to give us a negative 1x and a negative 2x, and that's going to be a negative 3x, which again isn't a negative 6x. So what we conclude is this thing is not factorable. The technical term is that it's prime, just like prime numbers. Whoops. I don't know what happened to my capital R there. But just like prime numbers, a polynomial that can't be factored, it can't be broken up as a product, is also known as prime. Now what's interesting about this is that we can kind of flip it around and talk about something in letter C that's rather important. It says, what can you conclude about the zeros that are found using the zero product law or factoring? So think about this. If you're able to factor something, right? I'm just going to pull out something random like, x minus 2. Let's say that we were factoring something. This is not the problem that we're currently working on. But if we were able to factor this, right, doing a little bit of shortcut work, we'd get answers like 2 and negative 7, or even a little bit trickier if we had something factored like 2x minus 1 and x plus 4, right? We would get, from this one, we'd get x equals 1/2. From this one, we'd get x equals negative 4. All of these numbers are rational numbers, or rational answers, or rational zeros. But they're rational. They have no square roots left in them that can't be simplified. So the reason that we really want to know both the technique of completing the square and the technique of factoring is, number one, factoring is easier, especially when you're trying to get answers that are nice rational numbers. But there are many trinomials, like the one that we worked with in this problem, x squared plus 6x plus 2, that can't be factored. And then if you want to find their zeros, then you have to use a different technique. Okay? Completing the square being one of them. We'll see another technique tomorrow called the quadratic formula, which is really cool. Maybe not tomorrow, but in the next lesson. So I'm going to clear out this text, copy down anything you need to. All right, here it goes. Okay, let's move on to the next exercise. Ooh, leading coefficient not 1. Let's analyze the quadratic f of x equals 2x squared minus 4x minus 16 written in standard form. Letter A says find the vertex, or write the function in vertex form and state the coordinates of its turning point. All right, this is going to be a little bit harder because our leading coefficient isn't 1, so let's review how to do this. Completing the square only works if the leading coefficient is 1. So when it's not, what we do is we factor that leading coefficient out of the first two terms. And again, this is the way I do it, okay? Your teacher may show you a different way, okay? But I'm going to factor a 2 out. And then what I'm going to do is I'm going to complete the square inside of that parentheses. Now remember, we're going to take half of the b term, half of negative 2 is negative 1. We're going to square negative 1, and we're going to add it on. Now remember, this is what's really quite tricky. Now I want to subtract something, but I don't want to subtract 1, because what I really added was a positive 2, right? Because of that 2 sitting out here, I really added a positive 2. I know that's awfully tricky, right? But that means that we can rewrite this entire thing. Remember, I can now factor this trinomial as a perfect square. It'll factor as x minus 1 squared. I can combine the negative 2 and the 16 and get negative 18. So here's my function written in vertex form. Now remember, that leading coefficient of 2, although it made the problem harder, doesn't change the fact that my vertex can now easily be read by looking inside of the parentheses, looking outside of the parentheses. I have a vertex or a turning point at 1, negative 18. Now the beautiful thing is we've done the heavy lifting. In letter B it says find the zeros of the function using your answer from A. Great. So I'm going to take my answer from A, not my turning point, but the vertex form of my parabola, and I'm going to set it equal to 0. And instead of factoring, what I'm going to do is I'm just going to undo what's been done to x. So I'll add 18 to both sides. I'll get 2 times x minus 1 squared equals 18. I'll divide both sides by 2. I'll get x minus 1 squared is equal to 9. Oh, I like 9, right? Nice perfect square. Take the square root of both sides. I'll get x minus 1 is plus or minus 3. I know that's tricky. I'll get x minus 1 is equal to 3. Add 1 to both sides. And I'll get 4. And I'll do x minus 1 is equal to negative 3. Be careful here. Add 1 to both sides. And I'll get x equals negative 2. There we go. There are my 2 zeros, found by completing the square. We could certainly find them by factoring. And do you know why? Think about this for a moment. We could find them by factoring because the roots turned out to be rational numbers, not irrational. The only time we absolutely, positively have to use completing the square, I guess, is, well, in 2 cases. Number 1, the test asks us to. Or number 2, when the roots are irrational. That's when factoring isn't going to help us. But here we were asked to do it. Determine the function's y-intercept. Remember, y-intercept always occurs, is always the output when x is equal to 0. So the y-intercept tends to be an easy thing to figure out because all you have to do is put 0 in for x. Well, I'm going to actually put 0 into the original function, although I could put it into the vertex form. 0 squared is 0, times 2 is 0. 4 times 0 is 0, minus 0. Minus 16 gives us a y-intercept of negative 16. Finally, letter D asks us to draw a rough sketch of the function on the axes below. Label all quantities a through c. Now don't grab your calculator on this. We can actually draw this quite easily now. I like to put the x-intercepts in first. So I have an x-intercept at negative 2. I have one at positive 4. I've got a turning point at 1, negative 18. So maybe right around there. And now what I actually like to do is draw the parabola in. This is hopefully going to turn out okay, but we'll see. Well, it's not gorgeous, but we're working on it. And now I like to label the y-intercept of negative 16, right? With that information, we can actually get, let me put the 4 right here, we can actually get quite a good picture of what this parabola has to look like. It's got a minimum value at negative 18. We could talk about its range, etc. But that's all the problem asked us to do. So I am going to clear out the text. Why don't you write down anything you need to? All right, let's get rid of it. Last problem. A quadratic function is pictured and has a leading coefficient equal to 1. Let's make sure that we understand that terminology, right? So quadratic's written in standard form, y equals ax squared plus bx plus c. The leading coefficient is a, right? So what they're telling me in this problem is that my quadratic has this look to it, x squared plus bx plus c, all right? The first thing they asked me to do is write the quadratic in vertex form. Well, that's going to be not too bad. We can actually figure out what the vertex is. It's negative 1, 1, 2, 3, 4. Negative 1, negative 4. So in vertex form, it's going to just look like this. X plus 1 squared, remember how that works, minus 4. Okay. Now it says write it in factored form. Well, this is kind of cool, right? Here we're going to work our way backwards. Notice that we have zeros at x equals negative 3 and at x equals positive 1. Now, if you were using the zero product law or factoring to find those, you would have had to have had x plus 3 as one factor and x minus 1 as the other factor, right? That would have to be it. So there's our quadratic in factored form. Now the last letter, I want you to pause the video and really think about this. It says, how could you establish that these were equivalent functions? Okay, we're not only going to answer how we could establish it, but we're actually going to go ahead and establish it. So pause the video now and think about this. All right, well, there's a lot of different ways, all right? Maybe the fastest way would be to graph both of them, right? And if you graph both of them in your graphing calculator, what you would find is that they laid on top of each other. You'd only see one graph. But I'm going to actually show how to figure it out algebraically, all right? And what we're going to do is we're going to write both of them. We're going to write both in standard form. And if they both look the same in standard form, then they are the same. All right, so let's take this guy, y equals x plus 1 quantity squared minus 4. To write this in standard form, what we'll have to do is we'll actually have to multiply this binomial out, x plus 1 times x plus 1 minus 4. All right, I'm going to do double distribution, so I'll get x times x plus 1 times x plus 1. Don't want to lose that minus 4. Distribute, I'll have x squared plus x plus 1 minus 4. Now I'll combine like terms. We have two x's. I can combine the 1 and the negative 4, and I'll get negative 3. All right? Let's take a look at the one that's in factored form. X plus 3 times x minus 1. This one might be even a little bit easier because all I have to do is do the distribution. So I'm going to multiply x minus 1 by x. And I'll multiply x minus 1 by 3. Again, your teacher may have told you other methods, such as what's known as foiling. That's okay. Right? So distribute, double distribution, combine like terms, negative x, positive 3x is positive 2x. Don't have to do anything with that. And there we go. And notice, they're the same. Moral of the story, right? Moral of the entire lesson possibly is that quadratics can be written in a lot of different forms. They can be written in standard form, and ironically, that's the one that we typically see the most often. and yet it may be the least helpful. In fact, I'd say the only thing that the standard form is good for a quadratic is quickly identifying the y-intercept. Did you notice that? Right, one thing that you can definitely do with the standard form, and here we've got our y-intercept at -3, is we can sort of see that y-intercept. But written in vertex form, you can very quickly see the turning point, or the vertex. Written in factored form, you can very quickly see the zeros. All right, you might have to think about them a little bit, right? Because of the whole wacky, the sign changes thing. But overall, each one of these different forms has its own advantages and its own disadvantages. All right, I'm going to clear out this text one last time, so copy down anything you need to. All right, here it goes. Okay, let's finish up. Well, that was a nice lesson where we finally got to see where completing the square can be helpful. We are certainly going to get more work with this as we look at the quadratic formula and see how that gets developed, and as we do one final lesson where we put all the different methods that we've looked at together. For now, though, this has been another eMathInstruction Common Core Algebra 1 lesson. Don't forget to get a copy of the worksheet or the homework by clicking on the video's description. For now, I'm Kirk Weiler, and until next time, keep thinking and keep solving problems.